Okay, this is lecture 25 in 2025 by Harvey Friedman, and he will speak about invariant free choice. Please.
Yeah, actually, I should call it finite free choice, really. I'll tell you why. Um, yeah, so I'm starting all over because I have a better way to do everything. And uh, I spent all this time pretty much with some confidence giving a whole new development here. The details have to be worked out for next week, and I'll talk about more details next time. But I think I should get through this whole new way of doing this. Now, the goal is here to get explicitly pi zero 2 and explicitly pi zero 1, actually, sentences that are equivalent to con SRP. All right, so I've changed the title. I've changed some of these. I changed the ch last two chapters. I don't use the word invariance. Uh, I'm not using the word invariance, although it is really still invariance. It isn't. It's a little different than the invariance in invariant maximality. So that's why I want to maybe make the titles more general uh, by making the titles shorter of chapter 5 and 6. So we're talking about chapter 5 today, of course. Oh, by the way, chapter 4 has been put in final form on my downloadable manuscripts page. I spent a lot of time finishing up and excuse me, wrapping up details in chapter 4, which was the derivation section. And the derivation section actually turns out to be even longer than the long reversal section in which was chapter 4. Chapter 3, sorry. Chapter 3 is the derivation section. Chapter 3 has been put on the downloadable manuscripts page. And it's chapter 3 is even somewhat longer than chapter 4, which surprised me a little bit. All right. And chapter 3 has a lot of open issues. Chapter 4 doesn't. But chapter 3 has a lot of open research directions in there you can see. All right. So I'm going to call this finite free choice. So here is the new um, organization. Um, Upper shift commuting full free choice. This is the infinite part of the chapter, and this is the finite part of the chapter. And in the infinite part, the invariance notion is commutation. Since we're dealing with functions, commutation is very natural, even more compelling in some ways than invariance. Well, more compelling than invariance for functions, but of course it's in some sense the same. But the upper shift is particularly a compelling animal. The upper shift, oh yeah, and also I moved this whole chapter now is moved to Q, the whole space of rationals, um, rather than minus one one. Minus one one closed is very much the best way to do invariant maximality. But for this chapter 5, I go to all of Q. So there's a thing called the upper shift, which we'll talk about down here. The upper shift is a particular mapping from Q into Q. It's the identity on the negative rationals, and it's +1 on the non-negative rationals. So it's a total function. And it extends to any dimension coordinate-wise. So we have upper shifts on all the QK, all the Q to the K into Q to the K. And commuting with the upper shift is a very nice form of invariance. Commutation. All right. In order to handle this properly, I need the theory of elementary embeddings, which is very, which is an integral part of modern set theory, but only a special kind. Only the elementary embeddings that you can get out of the SRP hierarchy, only the ones you can get out of the SRP hierarchy, not stuff like a measurable cardinal. And oh, there's two O's here. This is not right there. So I have this concept of a free choice function that we actually did last time, and that's very familiar, kind of unchanged free choice function. But I use the word full to mean it's the total kind, because we're going to do finite forms down here, and I don't want to have there's certain conflicts of notation. So I have it set up here so that I use the word full to mean total. And then there's this notion of bounded that turns out to be important that we'll discuss. So there's a thing called full free bounded choice functions, and you always can get a full free bounded choice function. That we prove that. We're going to prove that. But then there's this thing called upper shift commutation. So that means commuting with the upper shift. That is F circle upper shift equals upper shift circle F. This turns out to be the master equation that drives the high strength. So we have a statement which is called order invariance slash full free bounded choice slash upper shift. And that's the fundamental, that's the first fundamental. There's a slightly simpler one that's coming. The first fundamental statement in the infinite theory here. And we actually prove that statement using an elementary embedding. The elementary embedding of the kind that come out of this out of here. The kinds that come out of here. Okay. And then we show that this statement implies an old statement from chapter 3 in invariant maximality. And therefore, between this and this, we have a proof and a reversal. This will give you a reversal because we already reversed this in chapter 3 and 4. We reversed this. We understood this to be equivalent to con SRP. And then we show that this bounded condition is not needed for the reversal because the statement without the bounded condition implies the statement with the bounded condition. That's very nice because I'm interested in any simplification I can get my hands on, right? All right. And so then from all this, we get what we want, which is that this infinite statement here, without the B, this infinite statement here is equivalent to con SRP over WKL naught, and it implies con SRP over RCA naught. Yeah. So you get what you expect. And that's the infinite theory, and that's nice. It's OI slash FFC slash US slash upper shift is a nice infinite statement in using functions instead of invariant maximality. Yeah. All right. Now we want to give the finite form. See, this is all set up to make a delicious finite form. So 5.3 is the delicious finite form. It's called OI slash FinFC. slash upper shift. FinFC means we're talking about a finite free choice function, a finite free choice function. Actually, I keep changing the titles here. Just a second. Why is this frozen on me? Not. Oh, I called it finite free choice. Yeah, that's okay. Yeah, I want to make sure the word free is in there. All right. So with this finite statement, we actually show the finite statement follows from the infinite statement, and that turns out to be very easy, as you'd expect. And then the finite statement for the reversal, we have to show the finite statement implies the infinite statement over WKL naught. And this is a like a compactness argument or finitely branching tree argument. Because this statement really, you take the limit of these things and you get the, yeah, but no, but this is much harder than I'm saying. You have to do that, but there is some hard work in there. There is some serious hard work in here. It needs to be checked carefully by me by next week. Yeah. And so from this and all this stuff, we conclude just what we want. I think that we only get, without more care, we only get that in primitive recursive arithmetic in PRA that this is equivalent to this. That our finite statement is equivalent to this. Now, this statement is, by the way, pi02, and we'll have a very friendly way, particularly friendly way of making it pi01, which actually I think uses some interesting ideas that have to be checked carefully by next week. So there's a lot I have to check, and I have a chance of checking all this carefully if I don't change the statements, if I don't make them better. That always takes well, that's what happened right now, right? I mean, I'm not doing the stuff I talked about last time because uh, I got something much better, right? So uh, let's hope it doesn't happen again, or let's hope it does happen again. If it's going to be much better than this, I don't know what it's going to look like, but let's hope and not hope that it'll happen again. Okay. All right. Introduction. I just sort of verbally gave it. All right. So the first thing is upper shift commuting. No, that's not supposed to be the first one. What is going on here? First one is elementary embeddings. No. This is right. Yeah, this is the master section. It's got all these subsections. Yeah, so this is right. Yeah. Okay. So in section 521, we prove in WKL0 plus con SRP that there's an elementary embedding J from M into M with critical point, meaning a critical point meaning there's a least point that's moved, where M is a countable model of ZFC plus V equals L. This will serve as our crucial set theoretic preliminary. So this is a set theoretic preliminary. I don't know. It's sort of partially, it's perhaps vaguely in the folklore. I'm not 100% sure whether I can get a reference for this, but I've actually sketched this out in various other things that I've done and thrown away. Now I have to bring this back. That this is equivalent to WKL0 plus con SRP, that there's an elementary embedding from some countable model of, see, this is a non-omega model, from some countable model of ZFC plus V equals L into itself. Yeah. All right. In the next section, so that's the set theoretic preliminary we need. In the next section, we define the full free choice functions for relations R. These are certain functions from Q. These are certain total functions from Q to the K into Q to the K. We also introduced the important boundedness condition. Uh, so we have the full free bounded choice functions. Okay, so FFBC is every reflexive symmetric relation on Q to the K has a full free bounded choice function. That we prove that in ACA prime. That's some extension of ACA naught, but it's not as strong as ACA. We define the upper shift and extended in the next section. We define the upper shift and extended it coordinate-wise to each Q to the K. And we say that F from Q to the K into Q to the K is upper shift commuting if and only if F circle upper shift is the upper shift circle F. This is in preparation. This is all set up to be in preparation for sections 5.24 to 5.26. Why don't I just say 7 maybe? Because I think there is a 7th. Yeah. Okay, now we greatly strengthen FBFC to our statement, our almost best infinite statement in the function in this setup. OI ordered invariant FFBC USH. Every order invariant reflexive symmetric relation on Q to the K has an upper shift commuting full free bounded choice function. Okay, and we prove this in WKL naught plus con SRP using the elementary embedding from section 521. Using the elementary embedding from section 521. Yeah, that's why we had that set theoretic preliminary. So this elementary embedding is a sledgehammer that you use to prove stuff. Very nicely, actually. All right, in section 525, we show that our statement implies con SRP over RCA naught. Yeah, well, we'll say more when we get to it. And then we actually derive. In 6, we show this boundedness condition can actually be eliminated. That's a little tricky, but I was worried about that because I didn't really want to keep the boundedness condition around for the best statements. So you can derive FFBC, the statement with the boundedness condition can be derived from the one without. Thus, we conclude that OIFFC upper shift, the order invariant full free choice, with the upper shift condition, commuting with the upper shift, is equivalent to con SRP over WKL naught and implies con SRP over RCA naught. See, we're leveraging heavily on chapters 3 and 4. Well, mainly chapters 4. Chapter 4, the big reversal. See, that we did. We don't have to do another big reversal. Okay. So let's get into this some more. So what kind of elementary embedding? Again, I mentioned it. There's an elementary embedding F from M into M with critical point, and a critical point is the least place that gets moved, least point that gets moved, where M is a countable model of ZFC plus V equals L. And it's going to have to be a non-omega model. Why is that? Let's see. All right, let's not worry about that. Well, I'm going to want to prove it from here. So I'm going to construct it. It'll be a non-omega model. Yeah. Otherwise, you couldn't possibly prove it from here. All right. So, and this elementary embedding thing, I give a proof in WKL naught plus con SRP. Yeah. To the extent that that's not hinted in the folklore, it's kind of interesting. By the way, it goes both ways, but we don't really care about the other direction. Yeah. I mean, I'll mention it. Yeah. All right. So now we have the full now let's get into the objects at hand. The full free bounded choice functions. So if you have any relation on any set X, it's reflexive and symmetric. We know what those words mean. Now a full R choice function is a G from X into X. And see, full means it's total, such that for every X in capital X, it chooses an element. It chooses a successor. And and R free is just what you know to be distinct things are not related. And a full R free choice function is an R choice function whose range is R free. So there's this tension between being positive about the value of a function. In other words, it has to be a choice function. There's this tension and this negative thing about the range being free. The two things have to coexist. That's what the power is of these gadgets are. Okay, so now we have the full free choice theorem. Every reflexive symmetric relation on, now why did I write this? This is wrong. On Q to the K has a full free choice function. I should say that this is true in any space capital X, but in general, you're not going to be able to prove it in RCA naught. You need Zorn's lemma. So there's a Zorn's lemma form of this. So this is provable in RCA naught. And this is silly. This is silly. In fact, maybe I'll just make this very general. Why don't I make this? Why don't I make this super general? Yeah, just X. Yeah. So this is straightforward. Simple stuff. That a full free choice function is idempotent, and the range is the same as the fixed points. You see, they're very nice objects. All right. You can actually get these in exponential time, in fact. I'm trying to remember why I needed CIFA. I have to go back and look at the if it's ordered invariant, reflexive, and symmetric. I used to do that with the chapter 3. And there's no reason why it can't be done in IFA. I don't think I need CIFA. I think I'm gonna brave it. Okay. I don't know why I put CIFA before. I'm just going to do it in case I forgot about something. Put it back. All right. Okay, now here's the notion of bounded I want to use that comes up. This is what the important notion that for all non-negative integers n, f maps minus infinity n into minus infinity n. So full free bounded choice says every reflexive symmetric relation on Q to the K has a full free bounded choice function. And this is proved without any use of order invariance on the relation. It's just this is true of any relation. But you need ACA prime. You need it. You see, you have to build one of these gadgets on the from minus infinity to zero. Then you need to build the extended to 0, 1, minus infinity 1, then extend it to minus infinity 2, and so forth. But extending these things requires some arithmetic comprehension, some jump. And so you're going to go out indefinitely for the jumps. This actually does sound a little more than I think this may be ACA, what's called the ACA plus. Yeah, this may be a little bit more than ACA prime. Yeah. Okay, let's not worry about that. Side issue. Okay, upper shift commutation. So the upper shift, as I said, this is the function which is the identity on the negative rationals and plus 1 on the non-negative rationals. So it has a a real heavy-duty singularity at 0. So, if I want to do propaganda properly, I will say something like this. Large cardinals come out of this kind of singularity in math. Now that's, of course, a gross oversimplification of things, but that jump there makes a big difference, you see. That it's the identity on the negative rationals, and at 0, it suddenly jumps to 1. And this is supposed to be so jarring that large cardinals drop out. Okay, so the upper shift on any Q to the K looks like this. The upper shift of P1 through PK is the upper shift of P1 through the upper shift of PK. Now, a function is said to be upper shift commuting if and only if F circle upper shift is the upper shift of circle F. And this actually is equivalent to an invariance condition of the kind that we've been talking about up to now. Namely, if it is a total function, if it is a function from Q to Q and K to Q to K, then it's upper shift commuting if and only if it's upper shift invariant in the sense of its graph. Okay. So you still really are talking about invariance, but a particular nice setup. Okay, the next thing we want to do is use the elementary embedding to actually derive our statement with the bounds, by the way, our statement. And this is an interesting proof. You get the commutation with the upper shift out of the elementary embedding. Yeah. Okay, and yeah, and so we proved both forms. Well, I mean, this is the one we proved, but this is worth stating also because we're eventually going to be wedded to this because we're going to show that this implies this. In other words, you get the boundedness for free. All right, so elementary embedding implies this. I'll say more about, I didn't prepare the comments so I'll say more about how that works. The idea is that the elementary embedding that comes from that section becomes the upper shift, not the upper shift on a copy of the rationals that's Q cross -1 to 0. See, that's dense. Yeah. So you have to make a correspondence. There's a correspondence that you can make between the upper shift. This elementary embedding will give you a good upper shift that preserves a lot. And that's how the theorem 5241 is proved. Now, in next section, we want to talk about reversals. So how do we reverse this? So what we want to do to reverse it is pick a statement in our, remember we analyzed 16 statements in chapter 3 and showed they were all equivalent to Con SRP, right? So I just picked my favorite one for this purpose, namely this one here in chapter 3. And I want to prove this statement here. I want to prove this statement using using this. And that goes through. It's sort of like the way when I did the thing the other way last time, that free choice functions, invariant free choice functions give you invariant maximality, sets that are maximal. This is very similar. Okay, so we have that with a bound, the FFBC with the upper shift, that actually does prove this maximal free set thing. For this, remember this invariance, this thing right here, from -1, 0, all the way up. All right, next we want to prove this, that having a free choice function, you can find another free choice function that has the boundedness condition. Well, the basic idea is you have to come up with a more complicated order invariant relation in order to get so that a regular one here for that one will give you a bounded one for the original. And the basic idea is sort of like this. We know that we can always have -infinity to 0 go into -infinity to 0 because that's actually a consequence of the original statement unchanged without putting any boundedness in it. And that's because the stuff below 0 is the identity function on it, are very simple. Then you want to argue that you can do it at any point. In other words, -infinity to 0 goes into -infinity to 0. Then why should -infinity I go into -infinity I? Because we have indiscernibility. I mean, we already have, according to the upper shift, 0 looks like I. But on the other hand, the statement is not quantifier free, it's a quantified statement. But you can fix that by making your invariant free choice do more. So that's roughly how this works. And so because of that, you can we don't have to put this extra boundedness condition. So that completes section 5.2. Okay, and that tells us that these are exactly what we like. We know that they're equivalent to con SRP. And yeah. All right, but now let's go. So now the highlight of all this is the finite form, the finite case. So what do we do? Here we are. So let R be an ordered invariant relation on Q to the K, an R choice function. So here we don't talk about full. It's not full. It is a function G from some E to the K into Q to the K, such that for all X and E to the K, X are G of X. And an R free choice function is an R choice function whose range is R free. Okay. So we no longer talk about full. We just allow us to have any domain like that. Okay, but now how do you define upper shift commuting when you don't have things total? Well, my favorite way of doing this, I think I'm going to actually prove that there's I'm going to give some equivalent forms of this that are equivalent to this, but here's the one that's easiest to remember. You want to say that F circle upper shift equals upper shift circle F, but you can't quite do that. uh, you can say that these two functions agree where both are defined. That's the weakest notion. That F circle upper shift and upper shift circle F agree if they're both defined. There's some related concepts, but and I worked that out. I just didn't have time to talk about all the variants of that are maybe different or a little different or equivalent. All right, so here we have the statement that here is our finite statement. Every order invariant reflexive symmetric relation on Q to the K has a finite upper shift commuting free choice function mapping the numbers 0 through K to the K into its domain. See, there has to be some serious pizzazz in this free choice function. It can't be uh, silly just sitting there. It has to have some substance to it. So the way I say it is that it maps 0 through K to the K power into its domain. Remember, its domain has to be of the form e to the K. See? All right. So this statement is very cleverly saying that you map it from one cube into a bigger cube, which means that you can go further with a function because this is the domain after all, and the function is defined on its domain. Every function is defined on its domain. Yeah. All right, so that's supposed to be the magical statement. Now that's obviously pi 0, 2. Now I think I can make this explicitly pi 0, 1. It's very nice to do this so it's as pretty as possible, and I think I've got it. Every order invariant reflexive symmetric relation on Q to the K has this is all the same, has a finite upper shift commuting free choice function mapping 0 to the K into its domain. So far, it's 100% the same, comma, with field blah. And I have to check, I think I can do this, that I can actually tell you exactly what the field is. I can specify what the field is. Question mark is just going to be some big quantity. Question mark of K, it's not going to, it's just going to be. What did I do here? With field 1 over J such that the absolute values I see. Less than or equal to question mark of K. Yeah. Maybe I should make it clearer here. To the kth power. The field of a function is the union of its domain and range. So if I tell you what the field is like this statement is now obviously pi 0, 1, right? Because I'm asking for a function with only a bounded number of possibilities for things, right? So it's not a problem. Okay, so I think this is quite nice. Every order invariant reflexive symmetric relation on Q to the K has a finite upper shift commuting free choice function mapping 0 through K to the K into its domain with field blah. With field blah. And the claim is that this is easy, that the infinite form, the full form gives you the finite form. You just take a function, and then you just take the skull of Hall, so to speak, take the value, you take its image under 0 through K to the K. Yeah, so there's nothing to do there. But the other way is more interesting, of course. So how do you go from this finite statement why am I messing this up? This is supposed to be the other way. Yeah. Messed it up. Yeah. Okay, how do you go from the finite to the infinite? That actually is quite tricky. I've known this kind of proof that I'm plugging in here for some time. And about how you actually go from such finite statements to infinite statements. I'd have to prepare something to actually explain more about how I do this, but it's got to be checked by the next week. And I think everything will get checked as long as I don't improve this. Then I'm in good shape. And the ultimate is that I may need PRA instead of EFA and so forth. That's possible. But anyways, PRA proves that we have an equivalence. All right, so I think that's all I want to say today. And all this has to be completely worked out next week. And I think that, I think that this is pretty much, I don't really see how I'm going to improve on this because it's rather neat. Yeah, so the statement is every ordered reflexive symmetric relation has a finite upper shift commuting free choice function mapping this little cube into its domain, which is another bigger cube. All right, Andreas, I think that's it.